I'm going to explain what geometric mean is and compare it to arithmetic mean, and then how that relates to similarity in right triangles. So first of all, with arithmetic mean, if you have two numbers, and we call them A and B, and we don't know what they are, they're A and B for now. The mean, which we call M1, to go from A to M1 is D, to go from M1 to B is D, so it's the same amount from A to the mean and the mean to the B. And so if we want to solve for the mean, we can say because these are both equal to D, B minus M1 is D, M1 minus A is D, so they're equal to each other. I can add A to both sides, add M1 to both sides, I get to here, divide by 2, and you get this familiar formula that the mean is you add up the 2 and divide by 2. So add up A plus B and divide by 2. So in the case of 4 and 16, you have 4 plus 16 divided by 2, 20 divided by 2, so the arithmetic mean is 10, just the average, you might say, usually do. For geometric mean, rather than having the same amount to add to each one, you have the same amount to multiply. So to go from A to M2, you multiply by some number R. To go from M2 to B, you multiply by some number R. So what that means is that if I do B divided by M2, I get this R, and if I do M2 divided by A, I get the R, so that means they're both the same as each other. So now to solve this for M2, I cross-multiply to get to here in red, and I have A times B is M2 squared. I take a square to both sides. So now the geometric mean, instead of adding and dividing by 2, you multiply and take the square root. So what you would do is take the square root of 4 times 16, which is the square root of 64, which is equal to 8. And so as you can see, arithmetic mean, to go from 4 to 10, you add 6. To go from 10 to 16, you add 6. So it's the same thing. Geometric mean, to go from 4 to 8, you multiply by 2. To go from 8 to 16, you multiply by 2. So that's the same thing. That's the whole idea. So here we have this situation again. 10 was our value. And add 6, 8 was our value, multiplied by 2, multiplied by 2. So these are the same addition, same multiplication. Here's some more examples. All right, you have two numbers, you want to find the mean. Now this is for geometric mean only. So you do the square root of the two numbers multiplied together. So that's the square root of 400, which is equal to 20. And as you can see, going from 5 to 20, you multiply by 4. 20 to 80, you also multiply by 4. Over here, the square root of 6 times 9, which is equal to the square root of 6 times the square root of 9, or 3 radical 6. So this is 3 rad 6. Now, in this case, we're given a number and a mean, and you want to find the other number. Now, you can use the geometric mean formula, but it's easier if you think about the idea that to go from one value to another, you're multiplying by the same amount as going from the mean to the other value. So to go from 7 to 35, you multiply by 5. So to go from 35 to the other number, you also have to multiply by 5. 5 times 35, 175. In this way, to go from 50 back to 10, we're dividing by 5. So to go from 10 back to some other number, you also have to divide by 5, and so you get 2. So that's how we can find the third number if we're given a first number and the mean. All right, so now how does this all relate to right triangles? All right, this is where it can start to get more complicated. What we have in this page here is we have a right triangle. The right angle is at angle C, and then we draw an altitude from the right angle. So what happens is this is a right angle, and right angle, right angle. Okay, so what I have here, now I'm going to come over to the right side. We'll get down to these equations later. When I come over to the right side, and I look at the big triangle, the triangle on the right side here, which is ACD, and the triangle on the left side, which is CBD. So I've got the big triangle, the right triangle, and the left triangle. And this box means right angle, 1/ angle, and 2/ angle. And you know that if you add all three together, you're going to get 180 degrees. So in the big triangle, angle C is the right angle. Angle B is the 1 arc angle. Angle A is the 2 arc angle. All right, now let's look at the triangle on the right side. On the triangle on the right side, angle D is the right angle. Angle C is the 1 arc angle. And therefore, angle A must be, okay, we know angle A is a 2 arc from the big one, so therefore angle C must be the 1 arc because we know they have to add to 180. Looking at the triangle on the left, angle D is a right angle again. Angle A is a 1 arc. We knew that from the original triangle, and therefore if we've got a 1 arc and a right angle, we know this little one must be a 2 arc, so DBC. So by AA similarity, triangle CBA is similar to triangle DCA, is similar to triangle DBC. So this allows you to set up some proportions, such as CB, so first two letters, divided by DB, first two letters, is equal to BA, second and third letter, divided by BC, second and third letter. So we can make this proportion. Going over to our big triangle then, CB, that distance is distance A, DB is distance of X, and BC is a distance of A. So we have A over X equals C over A, and so if we cross multiply, you end up getting that A is the square root of CX. So what happens is A is the geometric mean of C and X. Now, the way we state this in terms of theorems is that this leg of the right triangle is the geometric mean of the whole hypotenuse, which is C, and the part next to it, which is X. Likewise, this leg is the geometric mean of the whole hypotenuse and the part next to it. So B is the square root of C times Y. You can also set up a proportion so that you see that the altitude is the geometric mean of these two parts of the hypotenuse. Now, this leads to Pythagorean relationships. So besides having these geometric mean relationships, we also have all these Pythagorean relationships, because for these three right triangles, they all follow the Pythagorean theorem. So these are all the different equations that we would use to try to solve these problems. They're all based on this idea of similarity. So here are several examples. First, a couple more geometric mean examples. Square root of 32 times 8, which is equal to the square root of 256, which is 16, which makes sense because to go from 8 to 16 multiplied by 2, 16 to 32 again multiplied by 2. Number 3, square root of 11 times 7, so that's just rad 77, can't simplify that. Number 5, square root of 10 times 20. The easiest way to do it is to rewrite the square root of 10 times and then make 20 into 10 times 2, so this is 10 radical 2. Okay, going over to this figure and looking at proportions now. So we're about to get to the use of geometric mean, but using proportions, again, we've got the smaller triangle on the right, smaller triangle on the left, and the big triangle. So just comparing sides, A over C equals Y over something. So A is the little side in the big triangle, C is the big side, so little over big, and then here's the little side in the triangle on the right, and the big side is A. And so the answer would be A. And so what you see is that if you were to solve this, you get A squared is YC, so A is the geometric mean of Y and C. Okay. Looking up at number 8, let's erase this, we have A over B, so shortest side, middle side in the big triangle, so short over middle is equal to something over H. So H is the, let's see, B is the middle side in this big triangle. So H has to be the middle side because you have to go together the middle side. It's the middle side in the triangle down here, and the short side then is Y. So A over B short to middle is equal to Y over H short to middle. All right, now these problems are used solving the equations we derived earlier. So let me go back to that quickly. Just flash to those equations. So that's all of these geometric mean equations, and then we can also use Pythagorean relationships down here. So we're going to use those. So to do number 13, we can say that Y is the geometric mean of the whole hypotenuse, 9 plus 3, and the part next to it, which is 9. So the square root of 108, which is equal to, let's see, this is square root of 9 times square root of 4 times square root of 3. So that's 3 times 2 times rad 3, or 6 radical 3. And then if we want to get x, x is going to be the square root of the whole hypotenuse again times 3, rad 36, which is equal to 6. And what's interesting about this is that this side's 6, this side is 12, and this is 6 rad 3. So this turns out to be a 30, 60, 90 triangle. Okay, now for 14. To do 14, what we do is, let's first find Y. And so y is going to be the square root of 4 times 12, because the altitude is the geometric mean of the two parts of the hypotenuse, so that's equal to 2 times rad 12, which is 2 times rad 4 times rad 3, 2 times 2 times rad 3, 4 radical 3. If we want to find x, x is the geometric mean of the whole hypotenuse and the part next to it, so that's 4 times rad 12, because square root of 16 is 4, and again 12 becomes 2 radical 3 as it did below, so you get 8 radical 3. A few more examples. For this one, the altitude of the big triangle is the geometric mean of the two parts of the hypotenuse, so 3 is equal to rad 2x. Square both sides, and then divide both sides by 2, so x is equal to 9 halves, or 4.5. And then finally this one over here, let's see, we can find y by using the Pythagorean theorem, so 1 squared plus y squared is equal to 3 squared, so y squared is 9 minus 1, which is 8, so y is rad 8, which is 2 radical 2. So we'll call this rad 8 for now, might be easier to work with. So now to get x, I can say that the altitude, rad 8, is the geometric mean of the two parts of the hypotenuse, and I square both sides and I just get 8 is equal to x. So now this is 8. And finally, to get z, several different ways to do it at this point. I'll use geometric mean though again. The leg of the big triangle is the geometric mean of the whole hypotenuse, which is 1 plus 8, so that's 9, times the part next to it, which is 8. And so this is equal to 3 times rad 8, which is 3 times rad 2 times rad 4, which is equal to, let's see, this becomes 2, so 6 radical 2.